of cut edges. So the statement reads as follows: an edge UV element of the edge set of the graph is a cut edge, okay, if and only if E is not in a cycle of G. So an edge is a cut edge if and only if, okay, if that edge is not the part of any cycle in the graph G. Okay, so let's look into one example before proving the statement. For example, let's consider this particular graph. Okay, here we can see that, okay, these edges DE, okay, EJ and J and KL, they are cut edges. So if you remove any of these cut edges, the graph will become disconnected. Whereas if you remove any other edges, for example, if you remove this edge, okay, the graph will still be connected, and that is true for, okay, these edges, these edges and these edges, right? So we can see that those edges they belongs to different cycles in the graph, okay, and that's what this statement says. An edge is a cut edge if and only if, okay, E is not in any cycle of G. Okay, so let's go and prove this statement. Okay. Okay, so here we can see that the statement is in if and only if form. So here we have to prove both direction. Okay, so let's first prove this direction. So that says, okay, if E is a cut edge, then E is not in any cycle of G. Okay, so here we are going to prove this statement by taking the contrapositive of this statement. So the contrapositive statement, it is as follows. So if we have a statement like P implies Q, the contrapositive of this statement is negation of Q implies negation of P. And again, from logic we know that these two statements are equivalent. Okay, so P implies Q is equivalent to negation of Q implies negation of P. Okay, so now to prove this thing, okay, we can use the contrapositive to prove this statement. So here we are going to, in order to prove this thing, we are going to apply that technique. Okay, so we are going to take the contrapositive of this statement. So this is in that form. P, in this case P is E is a cut edge in E, and Q is E is a cut edge, and Q is E is not in any cycle of E. Okay, so the contrapositive of this statement is something like, if E is on a cycle, then E is not a cut edge. So let me write down the contrapositive of this statement, and after that we will prove that one. And because of the equivalence, P implies Q is equivalent to negation of Q implies negation of P. Okay, then we are done with this proof. Okay, so if the contrapositive of this statement is, if E is on a cycle in the graph, okay, then E is not a cut edge. It is exactly similar, same as negation of P implies Q. A negation of P is, okay, E is on a cycle of G. Okay, negation of that is negation of Q. A negation of P is E is not a cut edge. Okay, so let's go and prove this one. Okay, so if E is on a cycle, then E is not a cut edge. Okay, so let okay, E equal to UV be an edge. Okay, on a cycle say C. Okay, so the situation is something like this. So we have this edge E, okay, between this U and B, and this E is part of a cycle C. Okay, so that's what we assumed here, right? E is on a cycle and let that cycle be C. Okay, so let the situation be something like this. And this is, okay, this particular cycle is in our graph G. Okay, so let's delete this edge from our graph G. Okay, so we can see that in G minus E, okay, these two edges U and V are still connected. Okay, and that says this U and V are in the same connected component. Okay, so if E were a cut edge, in that case, okay, if we delete a cut edge, then the end vertices, okay, it must go to two different connected components. And here we can see that in the graph G, if we delete E, okay, U and V are in the same connected component because they are connected through this particular path of this cycle. Okay, so in G minus E, U and V are in the same connected component. Okay, and that says that this E is not a cut vertex. So if we were a cut vertex, then after deleting the cut edge, after deleting that cut edge, then the end vertices must go to two different components. So here we can see that they are still connected and they are in the same connected component. Okay, and therefore the E is not a cut edge. Okay, so that's the proof for this direction. Okay, and let's go and prove the other direction. So the other direction, it reads as follows. Okay, if E is not in any cycle, then E is a cut edge. So again we are going to use the contrapositive of this statement to prove this one. So the contrapositive of this statement reads as follows. Okay, if E is not a cut edge, okay, then E is on a cycle in the graph G. Okay, then E is on a cycle in the graph G. Okay, so we are going to prove this statement here. Okay, so here we assume that E is not a cut edge. Okay, so let E equal to UV and E is not a cut edge. Okay, since E is not a cut edge, we can say that removing this edge, it won't disconnect the graph. Okay, so if you remove this edge, again we can see that there will be a path from U to V. Okay, so since this E is not a cut edge, then in that edge deleted graph, okay, G minus E, there is a path from U to B. Okay, and moreover we can see that these two vertices U and V are in the same connected component because there is a path from U to V. Okay, so let's call this path, okay, let that path be P P. So in this case the path is from U to V, so it starts at U, okay, and it goes to V using some number of other vertices. Okay, we do not know the length of this path. Okay, so here the situation is something like this. So we deleted this edge, so we have this graph. Okay, so let's look at that situation here. So this is our G minus E. In that graph we have something like this. Okay, U, V. So we deleted this edge, and here since that E, okay, so let me draw that edge in dotted line. So we deleted this from our graph G to obtain G minus E, and here we have, okay, since this E is not a cut edge, then there will be a UV path, and we call this path P. Okay, so let's go back to G and see what is going to happen. So here, okay, in G, so in G, so we can see that if you, okay, if we combine this edge and this path, so if we take this edge and if we combine with this particular path, okay, then we have something like this. Okay, so using this edge you can move from U to V, okay, using that edge, and using this path P. Okay, that's what this means. Okay, E followed by this path, then from V, okay, you can use this path to go back to U. Okay, and this is a cycle. It starts at this vertex U and ends at the same vertex U. Okay, so here we have this cycle. Okay, so you start from here, okay, you move to this V using this edge E, then after that following this path you move back to V. So here we have this cycle. Okay, so then E, this deleted edge combined with P in our original graph, we have a cycle, and that's what we are trying to prove. Okay, so this is a path. So in G there is a cycle, okay, that contains that particular edge E, and that cycle is this one, E followed by this thing. Okay, and we are able to prove this direction also. Okay, and hence the theorem. Okay, so that says an edge is a cut edge if and only if E is not in any cycle of G. Okay, so we will prove more properties of cut edges in the next few videos.